So what we're going to do now is talk about this last part of pharmacokinetics, or the last part of chapter 3, which is looking at dosage regimens. And we'll start our discussion by looking at continuous infusions. Now typically when a patient is in the hospital, you'll see them connected to an IV, and that IV is connected to a little box, and that box its job is to very slowly over time give a particular drug to the patient. And it does this because it can control the amount of drug in the patient and make sure there aren't major fluctuations. And so if you start an infusion there, what happens is that the plasma drug concentration is going to increase. And as the plasma concentration increases, the rate of elimination will also increase because they are proportional to one another. And so the concentration will increase and increase until it reaches a steady state. And at this steady state, the rate of infusion is going to equal the rate of elimination. And essentially the concentration won't change anymore. And then, as we know, if we stopped that infusion right there, we would see this first order, we're assuming it's first order elimination kinetics. And we know in the past that it takes about 4 half-lives for us to go decrease about 97%. So just kind of notice here the units for the denominator here. This is time in terms of the number of half-lives, and the x-axis here is the percent maximum of the plasma concentration. So if I stopped it here, 2 half-lives, 4 half-lives later, I've lost about 97% of the drug. You're familiar with that from Dr. Suchard. What you might not have been familiar with, though, is that it takes the same amount of time, for about 4 half-lives, to reach the about 97% of the steady state concentration. And this is what I've listed here. The number of half-lives to reach the steady state plasma concentration of drug equals the number of half-lives for elimination. So the first question I wrote here is how much time does it take to reach steady state? That's about 4 half-lives. The second question here is, what do we do if we need to achieve the therapeutic concentration rapidly? So let's just assume here that the half-life was 4 hours. Well, what that means is that I'm not going to achieve my steady state concentration until a total of 16 hours. So what if this patient comes in and you're giving him a drug to stop, let's say they have ventricular tachycardia, they're having some major heart issue, and you need to give them a medication to get their plasma concentration up very quickly. Well, you don't want to wait 16 hours. So what you can do is you can give a loading dose. And so what a loading dose is essentially I give an IV bolus right here. And we remember that if you gave an IV bolus, the concentration would just kind of come down rapidly. And right at about 4 half-lives, it's about 97% eliminated, and then it eliminates. Now, remember here that the area underneath these curves is proportional to the amount of drug absorbed. So if I was going to kind of just rough by the back of the hand kind of calculate this, well, the area underneath this curve, let's call this A. And if I measured the area underneath this curve, let's just call that B. Notice that A essentially is like the other half of this. It essentially complements that. If I added those two together, right, let's just call that C is A plus B, I would get something like this. And so by giving this loading dose, we can reach our desired therapeutic concentration rapidly. Okay, I hope that makes sense. And what we'll do is we'll show you how to calculate this loading dose on the next slide. The next point here is how do we calculate this maintenance dose, and we'll also do that on the next slide. But I just want you to note here, to calculate that maintenance dose, we need to just be cognizant of the rate in has to equal the rate out. We need to be at this steady state. So, loading dose and maintenance dose rate definitions. So the loading dose is the dose required to quickly reach a particular concentration. We discussed that. It's with a single administration, and that administration is typically IV. And we're talking about a dose, so the units are milligrams. Now, this equation might be like, oh, I need to remember another equation. No, you don't. We've gone over this before. If we just remember that concentration, right, the plasma drug concentration is equal to the mass of the drug absorbed divided by the volume of distribution. This is essentially what we're looking at. And just remember here that the mass of the drug absorbed is equal to the mass administered, right, or the dose times the bioavailability divided by the volume of distribution. So if I rearrange this equation and I just solve for dose, right, or the loading dose, I get this loading dose is equal to the volume of distribution times the plasma drug concentration. I'm just bringing that over here. And I'm just dividing this by the bioavailability. So note that as long as we remember concentration is equal to mass over volume, and we remember our equation for bioavailability, it's a piece of cake. And oftentimes, whenever you're calculating a particular dose, what you'll do is you'll just divide by bioavailability in the denominator to help you account for if you're giving it IV or not. So if you're giving it IV, remember here, if it's given IV, the bioavailability, which I'll denote with F, is equal to 1. So the maintenance dose, how do we calculate this? Well, notice here I wrote the maintenance dose rate. So this is a dose over time. And essentially, if we remember, in order to be at this maintenance dose, we need to be at steady state, where the rate in is equal to the rate out. And by rate out, I'm referring to this rate of elimination. Now, in the last lecture, we covered what that rate of elimination was. We said there were two components of it. One, the most important determinant of the rate of elimination is the clearance. And then two, which was a constant for a particular drug in a particular person. And we multiplied that by the plasma drug concentration. Notice that's what we have in the numerator right there. So, and then essentially what I'm doing is I'm calculating a dose. So just like I did before, this mass absorbed is equal to the dose times the bioavailability. And I should make a note that this dose is over time, so I'll just write the dose rate. Well, if I'm solving for this, I just divide over the bioavailability, and I get the dose rate is equal to the clearance times the plasma drug concentration divided by the bioavailability F. So relatively straightforward as long as you understand where the equations came from. So the last point I want to make here before we do a little question is this idea of the therapeutic window. So here we've essentially reached somewhat of a steady state concentration. The steady state is somewhere around here. And we take the pill here, our concentration goes up, and as you metabolize the pill, the concentration goes down, and then you take another pill, the concentration goes up, and it kind of repeats over and over again. And so the limits of where you want this to go up and down, well, you don't want a concentration to be lower than the minimum effective concentration, and you don't want the concentration to be higher than the minimum toxic concentration. And so the difference between those two is what we call the therapeutic window. And so the narrower the therapeutic window, what this means in terms of drug dosing is, there's a couple of strategies here that you could have dosed this medication. If it's a narrow therapeutic window, what you're going to have to do is give more doses over a shorter interval. So if I gave more doses over a shorter interval, it would go up and then come down, it would go up, it would come down, it would go up, and then it would come down, right? And I would still be at this kind of similar steady state concentration, but I would have less fluctuation. Note if I gave a very large dose over a longer time interval, well then it would go, and if I wanted to be at that steady state, it would go up and it would come down, and then I would dose it again, and we'd go up and it would come down. Now I'm being a little over dramatic here, but notice that the larger the dose you give over a longer interval, I would still be at approximately the same steady state, but I might go above this minimum toxic concentration, and waiting for this to come down, I might come below the minimum effective concentration, but I could still be at the same, quote, steady state concentration. So really, there's always a balance between how frequently you want to give the drug and the fluctuations. And this is why continuous infusion is sometimes so beneficial, because you don't really have any fluctuations. You're breaking up that dose over a long period of time. So here is this last loading dose question that we're going to do here, and then we're going to jump into kind of the molecular components of metabolism, or chapter 4. So a man comes to the ED with ventricular tachycardia. He weighs 80 kilograms. The doctor decides to treat the man with an intravenous bolus dose of an antiarrhythmic agent to attain an initial peak serum concentration of 2 milligrams per liter. The volume of distribution of this drug is 1 liter per kilogram. What is the most appropriate loading dose of this drug for this patient in milligrams? So let's just write down the things we know. We know the mass of the patient, and that is 80 kilograms. We know what the volume of distribution is. And so before, when we talked about volume of distribution, we gave it to you in terms of a 70 kilogram individual, the average person. But clinically, they'll give it to you in terms of the number of liters per kilogram. So if you have people of different weights, you can do a better job of estimating what that volume of distribution is. So here we say it's 1 liter per kilogram. So if I was actually going to solve for this volume that this drug is distributing in, or the apparent volume of distribution, it would just be this 1 liter per kilogram, and this is an 80 kilogram individual, and so therefore I get 80. And this is the VD that I want you to use for this equation, or for this problem. The concentration, our desired plasma concentration, we know here is 2 milligrams per liter. And so what we want to do is solve for the loading dose. We want to solve for the dose. So we just essentially going back to, concentration is equal to mass absorbed over the volume of distribution. And when we rearrange this and include bioavailability, as we did on the last slide, right, the dose is going to equal the volume of distribution times the desired plasma drug concentration divided by the bioavailability. This is given IV, so this is 1. The volume of distribution we just said was 80. And let's make sure our units work out here. So this is 80 liters. And the plasma drug concentration that we want to reach is 2 milligrams per liter. So these liters cancel out. And the dose of this drug, the loading dose, is going to be 160 milligrams. So this is a legitimate clinical problem that, is good to be familiar with. A lot of times now computers will do some of these calculations for you, but this kind of brings everything in together.